Okay. Yes, well, thanks everyone. I'm going to talk about our climate scenarios, which we've produced as a data set called Chestscape, which is a high resolution climate data set. It's derived from UK-SCAPE 18, but we've extended it and enhanced it to make it suitable for modelling of high resolution climate change impacts in the UK. So I'm just going to tell you a bit about our motivations, how we made it, and then what the data set will look like. So next slide, please. So as James talked about a bit at the beginning, the SPEED project has brought together multiple areas of expertise in UK-CEH and in other organisations to make coordinated projections of climate change impacts in various different sectors. And in order to do this, we need consistent climate change data that we can use in each stage of the modelling process to drive our models. In order to do this, we had sort of several requirements for our data. So we wanted high spatial and temporal resolution so that it's sort of commensurate with our existing historical and observational products and knowledge about the UK. We wanted to look at transient climate realisation. So really, we don't just want an estimate of what the warming will be at the end of the century. We want to be able to follow the climate through from historical all the way into the future. We want climate projections that are consistent with historical data. So climate models are generally, you start running them in the historical period and let them run through to the future. And we want the modelled historical period to look as similar to the real historical period as possible. We want to look at a range of warming scenarios. So this is to tie in, because we're wanting to look at the RCP SSP framework. We want to make sure that we're using consistent warming scenarios with the SSPs, even if the UK isn't going to have what we do won't necessarily have an impact on global climate change. It will be part of a global SSP, which may do. So we basically want to have kind of consistent RCPs and SSPs to look at as our possible scenarios. We want an estimate of climate model uncertainty. So if you run the same climate model twice, or you run different climate models, you'll get different estimates of climate change. So we want to have a bit of an idea of how much our projections are uncertain due to the uncertainties in the models. And finally, we want data that is published and accessible, so that partly for reproducibility and partly because if we're sort of building kind of a framework that people could extend and use for other bits of research, we want to make sure that people can use the same climate data that we used to drive their models. So at the start of the project, basically, there was nothing existed that fulfilled all of these needs. So we have decided to make our own. So and we've made Chestscape. So next slide, please. So Chestscape is our data set that we've made to address, to fulfill all of these requirements. So it's a data set of 11 meteorological variables as net CDF format. It's 1 kilometre resolution and has daily meteorology from 1980 to 2080. We haven't run a climate model ourselves. What we've done is take an existing climate model output, so UK-SCAPE 18, and then we've enhanced that to make it suitable for our needs. So we've downscaled it, and then we've bias corrected it using an existing historical climate data set, which is called ChessMet. And then we've developed the full range of RCP scenarios, and we've taken 4 ensemble members from UK-SCAPE 18 to make a small ensemble for Chestscape. And then finally, this dataset will be published shortly on the CEDA data archive, so it will be available freely and publicly available for anyone to use for future modelling. So next slide, please. So as I say, we haven't run the climate model ourselves. What we've done is taken UK-SCAPE 18 climate projections and developed them. So UK-SCAPE 18 is really the sort of state of the art of climate modelling in the UK. This has been run by the Met Office, and they've developed and provided a wealth of different climate change projections in various different formats. And what we're particularly interested in is the climate model output that they've produced. So they've run the climate model at 3 different resolutions. They've run a global model at quite a coarse resolution. And within that, they've run a regional climate model, which is better parameterized for Europe and is a higher resolution. And then within that, they've run what's called a convection permitting model, which is just run for the UK and is such a high resolution that it can start to resolve some atmospheric physics that is otherwise parameterized in the other models. And that's much closer to basically the weather forecast model. It's that kind of scale. All of these models, unfortunately, have only been run for RCP 8.5, which is the most extreme emissions and warming scenario. The global model, they've taken the RCP 8.5 and then they've manipulated that to give estimates of other possible warming trajectories. So they've done RCP 2.6 and then 2 degree and 4 degree targeted warming scenarios. But this is just too coarse a resolution for us to really use for our impacts modelling in the UK. At the other end of the resolution scale, the convection permitting model is really the sort of resolution we want. It's 2 kilometres, and that's really good. But because this model is so computationally intensive to run, they've not been able to run it for a full century. They've had to run it. They've run it for 20 years and then have a 20-year gap and then run it for another 20 years and so on. So you can't follow the climate all the way through the century. So what we've done is to sort of split the difference, and we've taken the regional climate model, so this is the 12-kilometre model over Europe, and then we've downscaled it, bias corrected it, and then used, again, time shifting and pattern scaling to give us alternative RCPs, and that gives us our Chestscape data. Next slide, please. So, as I said, there are sort of 3 steps to this, which I'll tell you about very briefly. So we take ensemble members from the UK-SCAPE 18 RTM ensemble, we downscale them to 1 kilometre, we bias correct to historical data, and then for both the bias corrected and the non-bias corrected, we create the 3 other RCPs that don't exist in the UK-SCAPE 18. Ideally, we'd be able to do this for the whole 12-member ensemble, but once we do this, because the resolution's so high, it's sort of practically infeasible to deal with such large amounts of data. So what we've done is to be pragmatic and take just 4 members of the UK-SCAPE 18 ensemble, and we've taken them. We've chosen members so that they sort of cover the range of different climate change possibilities in the ensemble. So we've taken sort of the lowest and the highest warming, and then we've taken a couple in the middle which have different precipitation responses to the climate change. So this gives us a kind of an estimate of the range of the ensemble without having to sort of fill in all of the gaps. So we've got 4 ensemble members, 4 RCPs, bias corrected and non-bias corrected. That gives us 32 different realisations of future climate for people to use for their modelling. Next slide, please. So the downscaling is done using a methodology which is based on an existing methodology which we've used to create our ChessMet dataset, and that was done by downscaling MOREX observational based data at 40 kilometres down to 1 kilometre for ChessMet. So we've taken that methodology and then we've adapted it and updated it to work for UK-SCAPE 18. And what this does is, as well as just interpolating, it then uses empirical and physically based methods to account for local topography. So there are some variables like air temperature where we're using lapse rates, so it's cooler if you go up to the top of a hill. There are rainfall and wind. We use empirical data sets to say how the rainfall and wind speed distributions will be different for at different elevations. And then for the solar radiation, we're also taking into account the slope and the aspect of each grid box. So essentially having south-facing slopes being sunnier and north-facing slopes being shaded. And you can see here, it's a little bit difficult to see over Zoom. On the left is the 12-kilometre data from one of the ensemble members for one day. And on the right is our 1 kilometre air temperature. And if you're able to zoom in, you'll see that there's sort of finer scale detail, particularly in the Scottish Highlands where it's very hilly. Next slide, please. So once we've done the downscaling, we then looked at bias correcting the data. So even if you've got a very well parameterized climate model, because of kind of internal and long-term decadal variability, they're unlikely to reproduce historical climate exactly. So there's often an offset between models and observations, and the plots at the bottom of this slide show in grey and black 2 observational data sets for the UK, and then all the coloured lines are all the different 12-kilometre ensemble members in UK-SCAPE 18. And the overlap is basically 1980 to about 2015, and you can see that there's quite a difference in the air temperatures and in the precipitation between the observations and the ensemble. One thing you can do is just say, well, we don't mind if it's not getting it exactly right in the historical period. We just want to know what the difference the model will see between the historical period and the future, and that's so you would just look at the anomalies. But that doesn't work for all modelling situations. So the approach that we've used is to bias correct the data. So that's to try and take these model time series and shift them so that they're closer to the observations in the historical period, but then keep those adjustments through into the future so that you preserve the kind of the warming scenarios. So we've used our existing Chestscape data set, which, as I say, is observationally based, 1 kilometre, 19, and we've used the overlap period from 1980 to 2015. We've done the bias correction by season and by location, so we've done a different bias correction for each 1 kilometre pixel in the UK, and we've done this individually for each ensemble member. So once we do that, then our models will look closer to the historical period in the overlap. Next slide, please. And then so the final step that we do is to create our alternative scenario. So as I say, UK-SCAPE 18 only provided RCP 8.5, but we can use those data to give us an estimate of other warming scenarios if we assume that there's a linearity of UK climate change with global temperature. So that means that for a given increase in global temperature, we're assuming it has the same impact on UK climate, no matter whether you get there very quickly because you're going through RCP 8.5 and warming very quickly, or if you get there very slowly because you're in RCP 2.6 or 4.5. We're assuming that there's a sort of direct relationship between global temperature increase and UK climate change. And there are 2 methods for doing this. You can use time shifting, which really just means to find years in your RCP 8.5 that have the same amount of global warming as your target RCP, and then just pick those, substitute them in the right place and create a time series that way. Or there's pattern scaling, which means that for each variable you work out how much it would change for a given amount of global warming, and then you take your RCP 8.5 year and you scale it to the global air temperature that you want. These 2 methods, and actually what we've done is a combination of both. So we've used RCP 8.5, shuffled the years around to get our target RCPs, but that only gives us an approximation. It ends up basically having too high variability compared to what we'd expect. So we then use pattern scaling to adjust it closer to our target RCP. And we do that by, again, for each season and for each location in the UK, we do a linear fit between each of our variables and the annual global mean air temperature. And that gives us a map that says for every degree increase in global air temperature, you would expect this particular change in each of your variables. And in order to get our alternative RCPs, we use CMIP5 as a reference. So there are several models in CMIP5 which have been run for all of the RCPs, and we can use the comparisons between those to work out our time shifting and pattern scaling. So next slide, please. So once we've done all of that, we end up with our Chestscape data, and we've produced it in a gridded NetCDF format. So it's these 1 kilometre grids which are aligned with the OSGB Ordnance Survey projection. It's 650 by 1050 points. We've kept Northern Ireland is on the GB projection. We're not providing it separately on the Irish grid. The files are CF compliant, so they can just be read in standard software like Python or R just to get the data, but they can also be read by software packages that require geographic information to then project it onto a grid, project it onto the globe and do mapping. So we've been working hard on making sure that the files will be able to be read in a variety of different software, and that they should be sort of good to go for mapping and finding locations straight away. As I say, it's gridded NetCDFs. Once we've got our 4 ensemble members, 4 RCPs bias corrected and not, we end up with 16 terabytes of data. So that will be available and people can download it if they want, but it'll also be, once it's published in the CEDA archive, it will be available in situ on Jasmine for anyone who's able to use that. But then Mike's going to talk a little bit about possible alternative ways of interacting with it that mean you don't have to just download enormous amounts of data. Next slide, please. So yes, just a bit of a summary of our data set. We've produced Chestscape, which is 11 meteorological variables in NetCDF format, 1 kilometre resolution over the UK. It's daily meteorology from 1980 to 2080, but we have also produced different time averages. So we've produced the monthly averages, seasonal for winter, spring, etc. We've produced annual averages, which should be noted because of the way the climate model runs. The annual averages go from December to November, not from January to December, and that just means is just to make sure that we capture all of the data in the climate model. And we've also produced what we're calling time slices. So these are 20-year mean monthly climatologies at 10-year intervals. So from 1980 to 2000, we calculate the mean monthly values from 1990 to 2010 and so on. And those are, for example, being used in our land use modelling. We've produced 4 ensemble members and 4 RCPs for each of those. And there's just a time series on the right to show that they're, for one particular ensemble member, they are sort of, they compare well with the probabilistic RCP scenarios that have been produced by UK-SCAPE 18. We've produced bias corrected and non-bias corrected data, and we'll be making both available so that you can see what effect the bias correction has had. And finally, these will be published on the CEDA BADC archive, hopefully in the near future, so that you will be able to download them and use them if you want. And that's all I've got. Thank you very much.